Okay, welcome all to the new topic impact ionization and avalanche breakdown. Okay, so last topic we had discussed about Zener breakdown, and we had found that Zener breakdown is basically because of the tunneling current. Now here today we will discuss in this topic avalanche breakdown, and the main cause is impact ionization. So what is impact ionization? First, let's understand this. Here it is in this figure that is taken from period book. Period. The carrier generation via impact ionization. So what happens is that under a high electric field, so show you like this, one electron which is in conduction band that accelerates when it finds sufficient energy. So of course when you will be having electric field, the energy lines that will be slanted, okay, like this. So this electron generally accelerates and gains energy. Now it's when it's a kinetic energy, because V is increasing, if that is sufficient to the covalent bond energy of the crystal. What will happen is that if you see as a crystal, so we have these silicon crystal where all these silicon atoms are connected via covalent bonds, right? So one electron which was here in conduction band electron means free electrons. Valence band electrons means these are the bond electrons. Okay, so the electrons which are participating in this covalent bond, they are, so these are valence band electron, right? And this one is conduction band electron. So when it finds sufficient energy, it interacts with the covalent electron. So impact ionization is basically carrier interaction. Carrier carrier interaction. Okay. So when this interacts with this bond, what happens is that it knocks one of the electron and gives all its kinetic energy is consumed in knocking out this one electron. Okay. So this one electron is knocked out and a hole is created over here. And these electrons come into rest. So now it has no energy, kinetic energy, but at rest, this electron is also at rest. Okay, two electrons at rest and one hole is created. The same phenomena is depicted in this figure, that when one electron accelerates under some electric field means slanted energy diagram. Then what happens is that it creates, it gives its all energy, loses its energy to bring one electron from valence band to conduction band. Valence band electron means that was bound in the lattice and that is freed. So effectively now there are two electrons. Both are at rest. However, because The electric field is still there, so both of them they will accelerate, and if sufficient energy is gained, they will create another impact ionization. Okay, and they will create four electrons at rest. Okay, and they will create two more holes over here. Now these holes will actually accelerate this side. So holes are generally taken as bubble model, so they move upward the energy band diagram, and electrons they move downward the energy band diagram. So this is impact ionization. Now how avalanche breakdown happens because of this, the probability that one electron will have avalanche breakdown, that depends that in one collision it has sufficient energy equivalent to the covalent bond energy. Now this can happen only when sufficient electric field is applied. Okay, so number one thing is that sufficient electric field is applied. Now if you see it in terms of p-n junction, what happens is that we are applying a reverse bias. That means p is connected to negative and n is connected to positive. So we are having an electric field in this direction. So externally we are applying it. Okay, and during the junction, generally this junction width w, that depends on the doping concentration, but if it is of the order of 1 micrometer or more, then what happens is that uh, the average collision time, or you can say that the mean collision distance, that is around 10 to the power minus 8 meter, and width is 10 to the power minus 6 meter. Okay, so around 100 collisions one carriers have during this junction region, around 100 or even more if it is lightly doped. So that will, one electron will go through 100 collisions. Now what happens is that if the electric field is not sufficient, it is not very high, then the energy band will look like this. So these energy are not getting sufficient kinetic energy for low electric field, and they will lose this energy in thermal heating. So if you are applying a reverse bias which is not sufficiently high, then what will happen is that they will lose the energy provided by this external source in heating the junction, but current will still be only the reverse saturation current. Okay, is. However, if you increase the reverse bias, what will happen? The junction will look like this, like this. Of course, this is N type, so it will have Fermi level here, it will have Fermi level over here, right? So what happens is that during this uh, one mean collision distance d, okay, that is approximately equal to 10 to the power minus 8 meter, they will gain sufficient energy to knock down one hole, and they will create impact ionization. Once again, during just by 1d, it will have sufficient energy, right? So this energy is sufficient to break up bond. So they will create both electrons. They will actually create it, electron hole pair through impact ionization, and these holes will move this side. These electrons are actually moving this side. So let's assume there are n electrons. Of course, this n will be equal to very small. N is equal to ni square divided by p, or you can say that it is na acceptors, number of acceptors. P is equal to na on this side. So these electrons, free electrons, conduction electrons, they will move this side. Now, after first collision, how many electrons will be there? N. Let's assume there is a probability P that not all the electrons are actually creating electron hole pairs, but only P electrons are creating electron hole pairs. So N was already there, and plus a fraction of this N that is creating electron hole pair. So after one collision, this will be the total number of electrons at rest after one collision. After second group of collisions, they will have Np into P, right? After third, it will have likewise, okay? So Np cube and plus Np 4 and plus so on, up to, depending on the what is the junction width, okay? W by d mean, that will be the total number of collisions. Now this probability P depends on applied electric field E. If E is very high, probability of that each electron will create an impact ionization, so that will be high, okay, very close to 1. Otherwise, if E is small, this probability P will be very small. So the total number, if you see, let's assume there are n out, that is total number of electrons coming in this n region. So n out divided by, let's assume this was n input to the junction. That is called the multiplication factor, by how many factors the carriers have been multiplied. So that will be sum of all these. So that will be equal to n into 1 by 1 minus p, right? As sum of geometric series, let's assume it goes to infinity. Okay, 100 is quite a large number. Divide by n in is equal to 1 by 1 minus p. So this is the multiplication factor where P is dependent on electric field. So if applied electric field, if reaches the critical or breakdown electric field, then this P tends to 1, and this multiplication factor goes very high. In general, you can also write in terms of because E is proportional to the applied voltage, E is proportional to the reverse bias. So you can write it as 1 by 1 minus VR by V critical, okay, to the power n, some factor. That is how it is related. So this multiplication factor you can find directly from first principle, and people have found this exponent n as experimentally. So that is how they found it. Now here are the equations that how to find the critical electric field. As we know that the maximum electric field in a PN junction is at 0. If you remember this, right? Minus XP XN junction, and the electric field lines goes like this. Okay. So this is x is equal to 0. So at 0, this is the maximum electric field. And this expression is given by this equation. You can go and you can actually consult this textbook. These equations are taken from period book. Okay. So now you can write that if this is equal to the critical electric field for breaking the bonds, then at that time that reverse voltage can be called as breakdown voltage. And that is how we can find the breakdown voltage. You can see that breakdown voltage is proportional to Na plus Nd by Na Nd, because this is the constant for a given material. For silicon it will be a constant, for gallium arsenide it will be another constant, gallium phosphide it will be another constant. Of course, if Eg band gap is high, generally this critical electric field is high to break the bonds, and hence VGR is also increased. Okay, that is how we get high breakdown voltage materials. So you can see that the breakdown voltage is proportional to 1 by N. Apart from that, you should understand this graph also. This graph, okay, where the breakdown voltage is proportional to 1 by NB. You can see from this. You can also see that if the band gap of the material is higher, as germanium, silicon has higher band gap as compared to germanium, so it has higher breakdown voltage for the same doping concentration. Okay, so for the same doping concentration, you can see the silicon has higher breakdown voltage. Likewise, gallium phosphide for the same doping concentration, it will have higher breakdown voltage as compared to silicon. Right? This is how it is decided. And that's why for many applications, especially for a space application, we need uh, high breakdown voltage, because in space radiation fluctuations are quite high, and to survive your electronic circuits, it's very important that its breakdown voltage that should be very high. For high band gap material like gallium nitride, uh, zinc oxide, the breakdown voltage may go up to 1000 volts. Okay, of course, depending on the doping level. The doping level is minimum. Okay, breakdown voltage cannot higher breakdown voltage can be achieved. Okay, so I think I have completed this topic. Of course, generally this breakdown voltage happens only when if the Zener breakdown condition is not met. So if the Zener breakdown condition is met, then first Zener breakdown can happen. So that generally happens between 2 to 10 volts. In silicon, 2 to 10 volts. Okay, and if this condition is all the conditions required for Zener breakdown is not met, then ultimately this will happen at some higher voltage that ranges from 50 to 100 volts for silicon, and that will be avalanche breakdown. Just note that in avalanche breakdown, because it is very high impact on crystal, right? So all the crystal is damaged in this case, and that's why after avalanche breakdown your device will not be used as usual. Okay, so your diode is now burned, you can say. So after that you cannot use. And however, for after Zener breakdown, because the Zener breakdown is because of the tunneling current, and tunneling is a quantum mechanical phenomena, and that's why uh, the lattice is not destructed, and hence the diode can be used once you remove the reverse bias as a normal in case of forward bias case. Okay, that's why Zener diode can only be damaged if its power rating are violated. That means the maximum rating of the Zener diode, that is equal to Iz into Vz. If anyhow you are applying such a bias that this current is quite high, so that is, let's assume Iz max is equal to Pz max divided by Vz. If you are applying a reverse bias that is giving you more current, more than this rated current, then your Zener diode may damage. Otherwise it will work fine. Okay? I think I have completed this topic. I will meet you in another topic with new concepts. Thank you.